We begin with the zeroth law of thermodynamics. It is called the zeroth law because it was put together after the first and second law. And upon its realization, it didn't make sense labeling it the third law because it actually has precedence over the first and second, meaning that we need the zeroth law to be established in order to discuss the first and the second law of thermodynamics. So we're going to go ahead and talk about thermal equilibrium. And in order to do that, let's talk about some definitions. So we consider a container with a gas in it. The total energy of the molecules is called the thermal energy. And sometimes we call this, for us, we're going to call it internal energy. Internal energy is made up of all the energies in a system. In this case, we're going to be focusing mostly on thermal energy. And the average energy per molecule is related to the temperature of the gas. So when we talk about things of Celsius, Fahrenheit, Kelvin, that is temperature. Well, you'll notice, for example, if water is boiling, or if lava is boiling, you'll notice that there is a lot of movement, a lot of action. And so you'll notice that there's a high velocity. Now, if an object, or if a material or a fluid or a solid or a system has a lot of velocity in it, that means that it has a lot of kinetic energy because we associate energy with velocity, the kinetic energy with velocity. And so objects with more velocity would have more kinetic energy. That's what makes something hotter. Okay? So if all the molecules in a system are moving rapidly, then all the molecules in that system have a greater velocity, which means they have a greater kinetic energy. And kinetic energy ends up becoming responsible for making something hot.
Oh yeah.
What makes something cold would be quite the opposite. So if the molecules, if we were able to slow down the molecules, if we were able to slow down the kinetic energy and decrease the kinetic energy by decreasing the velocity, then this was what we consider something being cold or making something cold. So, you could have boiling water, but if you put it in the freezer, for example, those molecules are no longer moving as fast as they used to. Thermal equilibrium is a state at which the transfer of heat between two or more objects is equal and the objects are at the same temperature. Now, this is a very common thing that happens, and of course you would recall that equilibrium is the same as balance. So we're talking about things being thermally in balance. In other words, they have the same temperature and there is no heat exchange between them. So the zeroth law of thermodynamics states that experiments indicate that if two systems are in thermal equilibrium with a third system, then all of them are in equilibrium with each other. So, for example, cold-blooded animals, lizards, snakes, etc., these animals have the same temperature, internal temperature, as their environment. And so they are in thermal equilibrium with the environment. If it becomes too cold, then they become cold as well. If it's too hot outside, then their temperature matches that same temperature as well. So then they would be in thermal equilibrium with each other. In other words, that thermal equilibrium is when objects in a system have the same temperature and there is no heat exchange between them. In the case of a thermostat, an object on the wall, the science and the technology behind a thermostat has evolved quite a bit, but the idea is that you set the thermostat to a certain temperature and it will activate either your air conditioner or a swamp cooler or a furnace or a heater, and it will attempt to go ahead and set regulate the temperature in such a way that it'll either cool the house or warm the house to the temperature that you set. And then once it does that, it turns off the system. Food. So if you ever taken a hot bowl of soup or hot cocoa and you left it outside for too long, you came back and you realized it was cold. Well, it wasn't really cold. It was cold relative to its original temperature, but it released its heat to the environment, and so it would be what we call room temperature. When an item, an object such as food, is at room temperature, what we're really saying is that it's in thermal equilibrium and experiencing zeroth law of thermodynamics. Now, on a not so normal everyday example, we could talk about volcanoes, right? When molten rock, lava, or magma comes up from a volcano, it will give off heat to the atmosphere until that rock and the atmosphere are at the same temperature. So the magma then becomes pumice or obsidian. When two objects come in contact with each other, they transfer energy. We've talked about kinetic and potential energy as well, and what we call conservation of energy. This energy is called heat. Okay. This energy always flows from the hottest object to the cooler object. Always. The symbol for heat is capital Q, and the units are going to be joules. So we have heat. The symbol for the heat is Q, capital Q. The unit for heat is going to be a joule. Summary. So you may have heard of hypothermia. It's a condition where a warm-blooded individual, a human for example, loses their capability for what we call homeostasis. Homeostasis is the ability of an organism to maintain its internal temperature the same regardless of the environment it's in. So homeostasis would be something that cold-blooded animals do not have. Humans, on the other hand, are warm-blooded, and they therefore have what we call homeostasis. So when a human loses its ability for homeostasis and being able to regulate his or her temperature, they experience hypothermia. They become hypothermic, and they possibly become quote-unquote cold-blooded. Okay. One way to treat a victim of hypothermia is to carefully cuddle the victim in a sleeping bag. Explain how thermal equilibrium plays a role in the process of treating somebody with hypothermia. That is your summary.